Good day, good day. This is the third podcast of week 3 distance learning, and this one is dealing with voltaic cells still, but a new concept is being introduced, which isn't too hard of a one, otherwise it's the same thing we've been doing, and that's of inert electrodes. And I want you to think back to this word inert. I brought it up previously in terms of the salt bridge, and that the salt bridge contains an inert electrolyte, which means it has cations and anions that don't participate in the reaction. They're simply there to help balance out charge. Well, this is somewhat similar. An inert electrode is being used in a scenario where we need a solid that conducts the electrons without it actually participating in the reaction. So here's the dealio. We end up with some circumstances where the half reactions have oxidizing agents and reducing agents that are simply dissolved electrolytes, or they might even be gases, and we don't actually have any solid metals. If we don't have a solid metal, we don't have a good conductor that is present to act as an electrode. Now, in the circumstance where this exists, there's many examples, but I pulled up 2 just to give you an idea. Here's one of them, acidified dichromate half cell. So look at what's present here. We have the dichromate, we have the H plus because it's acidified, we have some chromium 3 plus ions, and we have some water. Not a single one of those is an appropriate solid electrode in any way, shape, or form. So that creates an issue. It's still an excellent oxidizing agent and could work very, very well in the context of a voltaic cell, and yet there's an issue with actually conducting those electrons. Here's another example, and I see I rewrote acidified dichromate. This is supposed to say the hydrogen half cell. Okay, so the hydrogen half cell in this circumstance has, again, look what we've got here, H plus ion and, hydrogen gas. So similar scenario, a decent oxidizing agent, not as good as the dichromate, but still decent, and yet no solid conductor to be found as an appropriate electrode. Good news is we have a solution to this, and this is where inert electrodes come in. And there's a couple that they found from a chemistry perspective that are both quite effective. One of them is graphite, right? Honestly, simple carbon, guys. That's what this is. And of course, those are the ones we would use quite often in the lab when we were doing labs on this. And the other one is platinum, which is kind of cool. This is platinum here. Platinum is very, very expensive. And we do have some platinum electrodes in the lab, but if you notice, we don't use a great big chunk of solid platinum because that would be insane amount of money. So instead, we spin it really, really thin, almost like a mesh or the coil, so that we can get the conductive properties in a way where we don't have to spend quite as much money. Now, that being said, the reason why both of these are such good choices is because the chances of them participating in a redox reaction are extremely low. So they work out well to simply conduct the electricity, the electrons, but to not actually be one of the oxidizing agents or the reducing agents. Okay, let me show you an example of how you could do this. Let's say that we use this voltaic cell, a copper and acidified dichromate voltaic cell. And if you notice, this copper would be a part of one of the half cells, and this acidified dichromate would be a part of the other half cell. The way that we do this is very, very similar to how we did the questions on the previous podcast, and that hopefully you tried to look at in your assignment for this week. So first things first is you have to list out everything. And this again is where things can sometimes get confusing to some people, because they'll list everything out and write out copper solid and figure, now we're done. Not at all. Find copper solid on your table. And when you do, what you'll notice is that you have to write down everything. So you're going to have to write down the copper solid, of course, but we need to write down the copper 2 plus as well because it's there. Okay, so speaking of which, comma, copper 2 plus aqueous is present. And then the acidified dichromate means that we have the H plus because it's acidified, the dichromate, the Cr2O7, 2 negative. And then similar type thing, if you go over to our page 7 table again and find that half reaction, all of this still needs to be written down. So yeah, we've got the dichromate, we've got the acidified, but you also need to write down the chromium 3 plus because it's present. It would be part of that half cell, and of course the liquid water. So let's list those in turn to make sure that you've got everything. Okay, I'm gonna run out of room here. So imagine that we've got our Cr3 plus aqueous and our H2O liquid. Now, regardless, when all those are there, we can still see that this is, of course, going to be our SOA. And then if you glance through your table, look for the reducing agent. Copper solid is the strongest reducing agent. Once you have those two picked out, that means that you can start to build your half cells and in turn then your voltaic cell. Remember, the SRA is where oxidation happens, so that copper solid is going to be at the anode. Here, technically, this is where reduction occurs, but there's no good choice there for a cathode, which means we need to use an inert electrode for the cathode. Which one will you choose? Honestly, if you've got the option of taking platinum, it's the best choice. If you have just where you gotta use what's cheap, well, then of course the carbon will work fine. But I'll usually turn to platinum, especially when I'm doing diagrams, just because, hey, why not do a best case scenario? Okay, let's start drawing this thing. Alrighty. First things first is similar to what you did before, where you'd have to take one of your beakers for one half cell, the other beaker for the other half cell, draw on your salt bridge. This needs just to be a given every single time. Draw in an electrode in each, even though one of these is an inert electrode, it still absolutely needs to be included in your diagram. And make sure that your electrodes are connected by a wire. If you want, you could even draw a voltmeter in there to be in the middle that we could figure out the voltage by if we chose to. Okay, next thing. Like I said, I tend to draw my anode on the left. That's just kind of a habit that I've formed through the years. So anode on the left, cathode on the right. And if you think back to what we figured out here, our copper solid is going to be our anode, which means that I can write my Cu solid over here. Now on the other side, the cathodes needs to be that inert electrode, which I prefer to use platinum when I can. If you chose to use carbon instead, no, that's no problem. Okay, in the salt bridge, always show what those anions are doing. Go into the anode. And vice versa, always show that the cations are going down to the cathode. In addition, our electrons are constantly flowing from anode to, of course, cathode. Okay, there we go. Last step of what needs to be put into here is what's happening in that oxidation reaction and what's happening in the reduction reaction. So to do that, we would show the copper solid is being oxidized into copper 2 plus ions, right? Oxidation reaction. Vice versa, and here's where this one gets a little bit different. I'm gonna run out of room potentially in here, so I'm gonna make it a little bit bigger just for the sake of my diagram. So here's my bigger beaker. There we go. What happens here when we draw this is we still take the reactants, which in this case is your H plus and your dichromate, your Cr2O7, 2 negative. And we draw dual arrows that come in together. It's a little hard to see on this diagram, so make sure you look at the notes. So that's an arrow coming as they meet, and as they come out, we get two products. So you write those here, H2O liquid, and of course the chromium 3 plus aqueous. The platinum is not participating in the reaction at all, which is why we simply have those dual arrows coming from the hydrogen ion and the dichromate ion turning into the water liquid and the chromium 3 plus ion. All right, from a diagram perspective, that's our full diagram. Now we're on to the next step where we need to write out the half reactions and the net cell reaction. So, okay, here's what I'm gonna do. I'm gonna erase it so I've got room here. If you needed to see this more, I'll just rewind the video. You can figure it out, no problem. Da-da-da. Okay, here we go. So checking this out, moving on into, let's do the anode first. So anode is, of course, the oxidation reaction. This is going to be our copper solid, which is going to oxidize into copper 2 plus aqueous plus our 2 electrons. Vice versa at the cathode, this is our dichromate half reaction. So we have the Cr2O7 2 negative aqueous plus our 14H plus 6 electrons, which is going to produce 2 chromium 3 plus aqueous plus 7 waters. And I got that right off of the table. Now remember, always make sure your electrons are balanced here. I have a total of 2 electrons being produced and 6 electrons being gained, which means I'm going to have to multiply that anode half reaction by 3 so that I have a total of 6 electrons for both. My net cell reaction then, which is the same thing as the redox reaction, is putting it all together. We have 3 copper solids plus Cr2O7 2 negative aqueous plus 14H plus aqueous, which is going to produce, again, times by 3, so 3 copper 2 plus aqueous plus 2 chromium 3 plus aqueous plus our 7 waters. And there you have it. From an observation perspective, focus in on the reactants and the products. And I talk more about these listed in the notes, and I have them on the next page, but let's just chat about them here. For example, whenever you've got something happening with hydrogen ions or with hydroxide, you need to start thinking about acids and bases, right? That H plus is definitive of acidic products, and it's being reacted away. So which means it's reducing. If you're reducing the H plus because it's reacting, that means that the acidity goes down. Less acidic, which means an increase in pH, right? A higher pH is less acidic. That's one observation. Another observation that we're going to go up or recognize here is that copper solid is being reacted, which means the mass of that copper, which is at the anode, so the mass of the copper anode is going to go down, guaranteed. Okay, another interesting thing that occurs is this dichromate is being reacted away. So the amount of dichromate is going to decrease. And at the same time, you're going to have the amount of chromium 3 plus increase. Well, this has implications. If you check out page 11. Okay, so look at this thing. Dichromate is orange. So the orange color is going to reduce. It'll be less. So it'll be pale orange and it'll then go even less orange. And we're increasing the amount of chromium 3 plus, which means this blue-green color is going to increase, right? So this will decrease. The blue-green color will go up. Logical. All right. The other side that you can look at this is with the copper. So if you consider that we are changing copper solid into copper 3 plus, or sorry, copper 2 plus ion. Well, check out that one. If you look at copper 2 plus is a blue color, which means that that blue color is going to intensify. Alrighty, there's your observations. I've listed them here. They are also listed in your notes. Do be aware that through all of this, that inert cathode, which in this case I used platinum, is totally not affected, right? It does not increase in mass. It does not decrease in mass. It is inert, which means it does not participate in any way, shape, or form. Its sole purpose is to facilitate the transfer of electrons. All right, folks, you can now do another one of the questions in your assignment. Complete number 5. You're only going to do A through D. Leave out E at this point. After the last podcast where we deal with cell potential, you are then going to be able to complete E with no problem, and you're also going to be able to go back to number 1 and complete D. Talk to you soon.